In this video, we are going to talk about the area of a sector, or the sector area of a circle with a central angle. Now, I strongly recommend that you go back and watch my previous video that talked about the arc length of a circle that had a central angle with theta. These two are very much related. I want to now try to take what the book gives you and translate it for you a little bit so you can see a beautiful picture of what that represents. In the following, A, this capital A, denotes the area of the sector of a circle of radius r subtended by the central angle theta. Alright, let me explain what this is. So imagine we have a circle. It has a radius r. I'm going to measure that from 0 degrees here with an r for my radius. And then we have a central angle theta. Okay, so this is going to be my theta right here. Now the book will use the letter T for theta, or you could use the Greek letter theta if you'd like to. And we're going to find the missing quantity in each of these pictures. But what is A? Well, A happens to be this area on the inside of this space. This is A. So inside here, this is going to be our area of the sector. So the sector is what's in green here. I will also call it sector area. Now, another way to think of it is to think of the toppings. So this is how much area the toppings would cover. So in the previous video, the arc length was the crust. Now the area of the sector would be the toppings. Now what we have to do is we have to assume the toppings are actually square, because the square means that we're going to have our units actually squared in any kind of area. So if our radius happens to be in feet, then our area is going to be in feet squared. So imagine we had a very, very big circle that was 12 feet across or 6 feet in this direction. Our theta was 2 radians, and we learned in the previous videos that a radian is roughly about 57.3 degrees, so 2 of these radians are about 120 degrees. So our t is 2 here. And luckily, our formula is written in terms of theta and theta radians. So to get our sector A, to get this inside toppings area A, we're going to use the following equation. A equals 1/2 theta, which is our measurement of that angle in radians, times the radius squared. So R stands for radius, which is the distance from the center to the edge of the circle, where the theta is the angle measurement in radians. So this first example is going to be the most straightforward one. So we have a radius of 6 feet. So to find my area, we're going to have 1/2 times our radians. So this happens to be 2, because here it is. And then my radius is 6 feet. So I'm going to put my 6 here and square it. Okay, so 1/2 times 2 is just 1, and 6 squared is 6 times 6, so that's 36. So this is 36 feet squared. Kind of a cool note about the units. You'll note that my radius was given in feet, so if I put the word feet inside of this little parenthesis here, feet times feet is feet squared. So kind of cool unit measurement things that come out there. So we have the area is equal to 36 feet squared. So that means that if you have a square that's 1 by 1, this is 1 foot square, there's roughly 36 inside of this area here. Now, obviously, the ones by the edge of the rounded circle would be kind of cut off and put onto other places. But if you could take all of this shaded portion out, you would have 36 of these squares you could reform if they were soft like Play-Doh. All right, so let's take a look at the next one. This one leads itself into a picture. What we have here is we have a circle, but we have an unknown radius, but we do know it's radian. And from the previous video, a quarter radian is like a quarter of 57.3 degrees. So we take 57.3, cut it in half again. It's a little bit under 15 degrees, but there's our t is equal to 1/4 or 0.25. That's going to be inside there. Now, this shaded zone inside there, we know that too. We know that the area of that sector is 6 centimeters squared. So what we're going to do is solve for this equation for the missing part, and the missing part for this equation is a. So if we look at this equation up above, we know that 6 is our a, and then we have 1/2. Our theta is 1/4. So 1/2 times 1/4, and we're missing our r squared. Okay, so 6 is equal to 1/2 times 1/4 is an eighth. Top times top, bottom times bottom, times r squared. Then, to get rid of this, we're going to multiply both sides by 8/1. If we multiply 1/8 times 8/1, what happens is that we have a simplification here that works out pretty nicely. So that goes away here, and that goes away here, and 8 times 6 is 48. Now 48 is equal to r squared. Now this problem is looking for a decimal of approximation up to 3 decimal spots, so we're going to take the square root of both sides. By taking the square root of both sides, then we have r equals plus or minus, but we're not going to worry about the minus since this is theoretically positive, since you can't have a negative measurement here. So we're going to take the positive value of the square root of 48, and that would be roughly 6 point, rounding to 3 decimal places, 928, and we have centimeters. And also, kind of a fun fact, if you take the square units and take the square root of them, you get just centimeters. So there you go. There you have your problem number 20. Number 21 does not lean into a picture that well. The reason why is because we don't know theta. So what we know is we know our radius and we know our area. So let's just write down the formula. A equals 1/2 theta in radians times our radius squared. So here's what we know. We know that our A, which is our area sector, or sector area is 8. And then we have 1/2, and theta is unknown. I'm going to move the theta to the end here, but we do know that my radius is 6. So I'm going to take my 6 and square it. So you can reorder these multipliers here, because multiplication is commutative. I'm going to continue to write this problem over here and simplify it a bit more. So this is going to be 1/2. The 8 is equal to 1/2 times 36 times theta. And 8 is equal to, let's see, 1/2 times 36. That would be 18 theta. And then I'm going to divide both sides by 18. Now, if I divide both sides by 18, I get 8/18 is equal to theta. And I can simplify that even more by simplifying the fraction down to 4/9, which is equal to theta, which theta then would be equal to 0.444. This is rounded to 3 places. Now the units in this problem are going to be in terms of meters, but this is a distance of our theta, which is in radians. So this is 0.444 radians. So if we were to draw a picture of this, which we now can since we actually have our radian measurements, we know our radius, and our radius was our 6 meters. We knew our area, but now we can put that in with our theta, or t, being our 0.444. Now, that is roughly 44.4% of 57 degrees. A little quick calculation would show me that that's under 30. So if we make an angle that's about under 30 degrees, so our t is equal to 0.444, this shaded area right here would be roughly 8 square meters. So to end this problem, to end this video, we are going to take our equation of a equals 1/2 theta times r squared, and we're going to see what makes this a very tricky problem, because it seems like it's very straightforward. I mean, here we have a circle, and the circle has a radius of 3 meters, and it has a 120 degree theta, or t. Now we just need to find the space on the inside for the area of the sector. We'll see that this is the problem, because this equation that we have, the 1/2 theta r squared, it assumes theta is in radians, not degrees. So they gave us the degrees here. So what we have to do is we have to take our 1/2, we have to plug in our 120 degrees, but then multiply that by pi over 180 degrees. And that gives us the conversion from degrees to radians. And then we can plug in our radius and square it. So this is going to be, now let's do a little bit of work here. 1/2 times 20 is 60. And then we have 60 times pi over 180 times 9. Let's see, what do I want to do to simplify? Well, let's divide these two, simplify this, because if we divide 60 by 60, we make 1, and if we divide 180 divided by 60, we get 3. So now what we have is we have 9 pi over 3, which is the same thing as 3 pi, because 9 divided by 3 is 3 over 1. All right, so if we multiply 3 times pi, what we get is 9.425, and since this is what we're finding here, is we're finding this a, this is in meters squared. That is so this is pretty impressive, because if we had a meter by meter square, which is pretty big actually, a square meter is a lot of surface area, we would have roughly 9 of those inside of this shaded zone inside here. So there's roughly 9 of these squares inside of that yellow piece. Well, thank you for watching this video on the area of a sector, or sector area.